All right, so we are talking about volume now. So the idea is we're going to take some kind of a solid figure and we're going to use integration to figure out its volume. Sometimes we're going to have to create the figure. Sometimes the figure is going to be given to us and we're going to just figure out its volume based upon what's already given. Okay, the first part we're going to do today is we're going to take something and we're going to show how to actually create the volume of the solid. We're going to create the solid and then find its volume. So, this is one of our applications of integration. Last time we talked about how to find the area between two curves. Now we're going to figure out how to find the volume if we take a curve and we're actually going to create a three-dimensional solid. So calculating the volume of a three-dimensional solid. If a plane is revolved about a line, the resulting solid is called a solid of revolution. And it's because we are revolving something around a line. And we'll show this graphically. And the line that we revolve this around is what is called the axis of revolution. So let me kind of show you a graphic. Hopefully this will work. We'll see. Okay, I can't use the board, so I'll have to use the mouse. Show you guys a graphic of what I'm talking about here. No. Here we go. All right. So what you can see is I've got this equation, y equals the square root of x, which is the black equation on the xy axis there. And I'm stopping it and I'm bounding it from 0 to 1. I'm not sure if this is going to let me write on it. Let's see. No, it's going to make me tilt it. I don't want to do that right now. Okay, so it's not going to let me draw on it. But what you should be able to see over here on the left, which is this region right here that I'm kind of touching, this is what the solid looks like. And if I were to drop the vertical line at 1, you can see that all this area in here would create some kind of a solid region. It would be basically an area between two curves, which is what we've been dealing with. Well, so if I take the area that is created in here, all this area, and I go back over to this graph right here, and whoops, and if I take that line that's created and I revolve it around the x-axis, so now this is going to create a three-dimensional figure. Let's see how this works. Whoa, I totally rotated the x-axis. Did not mean to do that. Wow, that's so weird. Whoa. Technical difficulties. It's actually kind of cool looking, but wow. I wanted to show you all this stuff rotated anyway, but it's kind of acting up on me. It's not going where I want it to go. All right, so let's try this again. Let's go all the way back. So if I take that line, y equals square root of x, between 0 and 1, and I revolve it around the x-axis, there we go. It looks like that. Now what they've done is they've placed that little red disc in there because what it does is that thing kind of looks like a, I don't know, like a little dome or something like that on its side. The idea is if I were to slice this thing, this solid, going from the origin, so going from here all the way out to, stop doing that, all the way out to here, oh, man, this is just not cooperating. There we go. Man. All right, so from the origin out to 1 basically is what I'm trying to get at. If you slice it vertically, what you should be able to see is that, now I do want to rotate it. Let's see if this works. No. No. Boy, this thing is really sensitive. weird. Okay, I'm literally trying to drag in. It's moving the opposite direction. It's like flying an airplane or something. I gotta get used to this. There we go. Oh, man, that is so weird. Okay, so if I take it and I rotate it a little bit so you can see, the cross section of that is a disc. It's basically a circle. Now, it does have a thickness to it, but we want to try and make those things so that the thickness is really, really super thin. And what you're going to be able to see, hopefully, is that if I take that disc and I slide it this way, the disc changes size the further and closer I get to 0. As a matter of fact, when it's at 0, there is no disc. And then the disc changes its size as we go further and further and further out towards the boundary of 1. But the general idea is I can find the volume of this solid if I take the circle or the disc that's in there and find its area and then add this disc and then add that disc and then add that disc and so on all the way until I get to the end. So if I want to, I can make those discs really, 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 really super thin, and that's going to be our dx. And if I want to add up a whole bunch of discs, which is really just circles, I'm going to add up an infinite number of circles because I'm going to make them really, really, really super thin. So I'm going to add up a whole bunch of circles, which is integration. We're going to add or sum all of the circles from one endpoint to the other endpoint. The biggest thing is that you got to realize the circles are all going to change size as we go. Okay. So as the number of disks or circles approaches infinity, the volume is going to become, if you look at this, it is pi r squared. Now we can pull the pi out to the front, which is why the pi is in the front there, but it's really just adding up a bunch of pi r squareds. So you could write it like this. Where your r is your radius, but your radius is going to be some kind of function of x in this case because it is going to be a horizontal axis of revolution. And then going in the other direction, if you wanted to revolve this thing around the y-axis, which you very well can, and we'll show that as well, you would have a vertical axis of revolution, but then your disks would be actually going up vertically, and that one they did not have a visual of, but it would be going from a y value to another y value, so the change of y would be vertical. So the axis of revolution would actually be vertical in that case. All right, so the best way to do this is really just to kind of get to some problems here and show you guys what's happening. Find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine of x about the x-axis. So for these few, I'm going to at least start to sketch these. You won't always be able to do so, but the more you can sketch, the better. So y equals the square root of the sine of x. Believe it or not, it looks just like the sine of x. It's just smaller because it's a square root. And we want to, oh, I forgot this has to be bounded. We're going to bound this thing from 0 to pi. Yeah, typo. I forgot to put the bounds in there. So it's going to be from 0 to pi. So from 0 to pi, square root of sine of x looks like this. And I obviously enlarged it to make it easy to see what's happening. Now if I take this region, let's see how well this works. If I take this region, yay, it's working, that's highlighted here, excuse me, that is a plane of some kind. It's a flat plane, it's two-dimensional. I'm going to take this and I'm going to revolve it around the x-axis, which, and I always write this, I just kind of do a little circle that shows that's the way I'm revolving it. I'm revolving it around the x-axis. Well, if I do that, the other side of this, when it becomes three-dimensional, is going to look like that. And if I were to go ahead and slice this thing, because I have to take all of the slices starting at 0 all the way up to pi, if I were to show one representative slice someplace in the middle of this thing, and it doesn't have to be right in the center, it could be anywhere, but the slice is going to look like this. You're going to slice it, and it's going to look like a little, like a circle or a disc. The biggest thing is, if I'm going to add up a bunch of disks or circles, which is the equation of a area of a circle is pi r squared, I need to know r. That's the most important thing. I need to know the radius. Well, you guys should hopefully know that the radius obviously comes from the center of the circle out to any point on the circle. Well, if I start at the center of my circle, which is here, a representative point on the circle is right there. Obviously, the further I go to the left and the further I go to the right, the circle's areas and the radii are going to change, because the radius here is much smaller than it was at the first one. The radius here is much bigger than the one I just drew. So the radii are going to be different sizes depending on where the circle is. But the radius is defined, in this case, by the function square root of sine of x. It is the distance from the x-axis or the axis of revolution out to the function. That is the radius in this case. So the biggest thing is we need to know the radius, and the radius here is the square root of sine of x. That's the radius of every circle from 0 out to pi. And it's going to depend on the x value to know exactly what the radius is. So in order to find the volume of this solid, kind of looks like it's going to be like a football, you're going to take an integral from 0 to pi, and we should label that this is the volume that we're finding, of pi r squared, and since it is a horizontal, our change is going to be with respect to x. It's a horizontal change, so it's a dx. We have now defined that the radius is the square root of sine of x, so we're going to plug that into our radius. So the volume is going to be the integral from 0 to pi of pi times square root of sine of x squared dx. And here's where, like in the beginning, it showed on the first page that you can take the pi out front because pi is a constant. If I square the square root of sine of x, of course, it just becomes the sine of x. And then I can take an antiderivative and use fundamental theorem part 2 to figure this one out. So I'm going to get pi. Antiderivative of sine of x is negative cosine x. And we'll evaluate that from 0 to pi. So the pi is a constant. I can keep that out front. If I plug in pi, I get negative cosine pi. Minus, if I plug in 0, we get negative cosine 0. And then we just have to simplify. So let's see, that'll be pi. Negative cosine of pi is negative 1, so that becomes positive 1. Minus cosine of 0 is 1, so that's negative 1, but that's a negative 1, so really that becomes 1 plus 1. So what we get is the volume of that solid is 2 pi. And it is a volume, so it would be some kind of units cubed. I don't know what the units here are, but that's what it would be. 2 pi units cubed. So if I take the square root of sine of x from 0 to pi and I rotate it around the x-axis, the volume that is created from that solid is 2 pi. Okay. As we go a little bit further into this, we're going to have to talk a lot about exactly how you find the radius based upon the differences between where the radii and the axis of revolution is, because that's going to be a big thing. Remember that a function is measured from the axis to the function itself. Okay, that's how a function is measured. It's from the x-axis, or if it's a function of y, it's from the y-axis to the function itself. Radius is different. The radius is going to be from the axis of revolution out to the function. Okay, and that that I state that because the axis of revolution may not be the x or y axis, and we're going to run into some of those. All right, example 2. Find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared, g of x equals 1, about the line y equals 1. So now we are revolving this around something which is not the x or y axis. It's the line y equals 1. So again, let's go ahead and sketch this. All right, 2 minus x squared, that is a parabola which opens down, y-intercept of 2. So it's going to look something like this. G of x equals 1, that's like saying y equals 1. So that's going to be a horizontal line. Looks something like this. And it's the region which is bounded by that. So if I want to bound that region, it's going to be this. Didn't work. Let's try again. It's going to be this space in here. Okay, that's the region that is bounded by those two things. So in order for me to do this, I'm going to need to know a couple things. One, I need to know the radius. Two, I need to know what it's revolving around, and obviously I'm going to need to know the bounds. Okay, well the bounds are obviously where these things intersect. We're going to have to find that. Let's find the bounds first. Setting the two of those things equal to each other. Let's see, subtracting 1 gives me 1 minus x squared. That's the difference of squares, so x is going to be plus or minus 1. Okay? It says that we are revolving that region around the line y equals 1. This is the line, right? Y equals 1 right there. So we're going to revolve it around that line. So when I take that yellow region and I revolve it around that line, it's now going to look something like that. And drawing one representative disk, which is always a good idea if you can do it, it's going to look like a circle, something like that. From there, hopefully you can clearly see that the radius of that circle is going to go from the center of the circle out to that function. That was not drawn very well. Let's try that again. A little better. That's your radius right there. So we need to actually determine what the radius is. Well, the radius does not come from the x-axis in this case. The radius comes from the line y equals 1. The function, however, is measured from the x-axis all the way up to here. That's the function. That is the 2 minus x squared function. The radius, however, is not that far. As a matter of fact, it is 1 unit less than that. So the radius is going to be 2 minus x squared, which is the function, minus that gap that I just highlighted. So the radius is actually 1 minus x squared in this case. Okay, hopefully you guys are following that. If not, rewind it a little bit, watch it again. Hopefully that'll make some sense. So I now have my radius. I have my bounds, so I know I'm going to integrate from -1 to 1. And we know that the function is 2 minus x squared. That's the part that's getting revolved around the line y equals 1. So I'm going to integrate from -1 to 1. And this is going to be my volume when I revolve it. I'm going to integrate pi r squared, because I'm creating a bunch of circles, dx. And we have the radius, we have pi. We should be able to fill those things in and figure out what the volume is. All right, so we have our r, which in this case is 1 minus x squared. So we're going to fill that stuff in. The volume is going to be pi times the integral from -1 to 1 of 1 minus x squared dx, which in this case means that we're going to have to FOIL that out in order to go ahead and take the antiderivative. So we're going to get pi integral -1 to 1. Let's see, FOILing that's going to be 1 minus 2x squared plus x to the fourth dx. So now we can take the antiderivative, which is going to be x minus 2/3 x cubed plus 1/5 x to the fifth, evaluated from -1 to 1. All right, let's plug all this stuff in. I know I'm going to have pi on the outside of all this. Plugging in 1, that's the easy one. That's 1 minus 2/3 plus a fifth. Plugging in -1, one thing you should see is that, well, there's a 1 there, there's a 3 there, there's a 5 there. It's all even power, so really it's just going to change all the fraction signs, because when I raise -1 to those powers, it's going to become negative, so that's going to become -1 plus 2/3 minus a fifth. Alright, like I said, I like to combine all of my like denominator terms first. So I'm going to have pi. I got a 1 minus a minus 1, which is 2. Now I'll go to my thirds. I've got -2/3 minus 2/3, which is -4/3. And then I've got 1/5 minus minus a fifth, which is plus 2/5. So it looks like we're going to have to put everything into terms of 15ths here as a common denominator. So that'll be pi times 2 in terms of 15 is 30 over 15. 4 in terms of, 4/3 in terms of 15 is going to be multiplying by 5 top and bottom is 20 over 15. And then plus, what's that going to be, 6 over 15? So 30 minus 20 is 10, plus 6 is 16, so we get a volume of 16 pi 15th units cubed. There you go. So taking that region that was highlighted, revolving around the line y equals 1, gave us a solid volume of 16 pi 15ths. All right, let's see what the next problem is. All right, so I think what we're going to do is I'm going to go ahead and stop this video here, and then I'm going to come back and move on to the next one. And by the way, we will not finish this entire packet. As a matter of fact, we're going to stop at a certain point, and you'll see when we get there. I'll tell you when we're going to stop, and we'll cover the other part in class. So let me go ahead and we'll stop this video, come back with a second video. I think we should be able to get the rest of this stuff in one more video.